Welcome back to multivariate calculus. In this video, we're going to be talking about tangent planes. In your previous study of calculus of a single variable, one of the most important applications that you found for the derivative was in finding the equation of a tangent line. And then several applications of the tangent line allowed you to continue onward from there. But very simply, if we have an arbitrary curve, let's try drawing that using a normal size pen. If we have an arbitrary curve and we want to create a line that is tangent to that curve at a point, the slope of the line is the derivative f prime at the point in question. So if we have our curve f of x, our point x equals c, we can set up our tangent line with a slope f prime of c. When we extend from a line, a construction in 2 dimensions, to a surface, a construction in 3 dimensions, we still want to have that same idea. But instead of being able to think of a line, we have to extend that into 2 dimensions and get an entire plane. All right, so with those ideas in mind, let me get my head out of the way. And let's recall that in order to write the equation of a plane, we want a normal vector and a specific point that the line goes or the plane goes through. And generally we want to name that normal vector n hat equals a, b, and c, and our point is going to be x naught, y naught, z naught. Right. It turns out that it's going to be a lot easier to look at a surface that is given as a function z equals f of xy than it is to look at an arbitrary surface. But actually, neither way is all that easy. So instead of thinking about things in those terms, I'm going to change completely my strategy for thinking about a surface. When we started talking about multivariate functions, we talked about functions of 2 variables, and the graph z equals f of x and y is the equation of a surface. And one of the tools we used for analyzing that graph was sketching the level curves. We also talked about 4 dimensions, 3-dimensional functions, f of x, y, and z. And the graph w equals f of x, y, and z is a 4-dimensional structure. And if you pick a specific value for w, you get a level surface. I want to do that here. So I want to look at some other function. I'll call it capital F to distinguish it. And I'm going to write it as z minus f of x and y. And I want to think about the level surface formed when f of x, y, and z is equal to 0. That is exactly the surface that we had in the first place. All right, if z minus f of x and y is equal to 0, that means that z is equal to f of x and y. We're going right back in circular logic. But there's a reason for thinking about it this way. When you're thinking about level surfaces, when you're thinking about the level surfaces as a way of describing the 4-dimensional shape, As the parameter changes, we're looking at the level surface when W equals 0. You can imagine that as some sort of three-dimensional object. As W increases, that surface is either going to grow or it's going to shrink. And at every single point on the surface is going to change either directly out or directly in. And so if we find the gradient, come on, there we go. If we find the gradient of our surface f of x, y, and z, we're going to have something that is moving perpendicularly to the surface, or when we're talking about surfaces, we tend to call it normal instead of perpendicular. Why do we have two words to mean the same thing? I don't know. The language of mathematics is kind of stupid. I blame the ancient Greeks. But because the level surface is changing directly out or directly in, depending on the direction of growth, at every single point, the motion is going to be normal to the surface. And so this gives us very quickly a normal vector for the surface. If we can write our surface as some f of x, y, and z, wrong thing to box, some f of x, y, and z equal to 0. If we're given z equals f of x and y, that's pretty easy. If we're given something else, it's not that bad there either. Take the gradient of this new function big F, and we have our normal vector. Look at a point that we care about and plug it in to the equation and to the gradient, and that will give us the normal vector and the point that we care about. We can write the equation of the surface. So for example, we might ask to find the equation of the plane, which is tangent to some surface, say z equals 10 minus x squared minus 4y squared. Right? Thinking to what we've talked about previously with quadric surfaces, we can recognize that this is the equation of an elliptic paraboloid, but that's not really important here. It is a function, z equals some function of x and y, and I guess I need a point. Right, so I want the equation of the tangent line when x is equal to 1 and y is equal to 1. I can plug those things into the equation. And the first thing I need to do is figure out that when x is equal to 1 and y is equal to 1, that means that z is equal to 10 minus 1 minus 4, which is 5. Right, so we know we have our point, 1, 1, 5, that we're going to be going through. And that's the first part of the battle. The second part of the battle is to find the normal vector. To find the normal vector, I write that f of x, y, and z, and just move everything from one side of the equation to the other. I'm going to have x squared plus 4y squared plus z minus 10, and that's equal to 0. All right, I just moved everything to the left-hand side of the equation of the function. Wrong button. Why is it erasing? Technology is really working well for me today. I apologize. All right, so I took that equation, I moved everything onto the left-hand side so the right-hand side is equal. I named that left-hand side as capital F, and now I'm going to calculate the gradient of F. The x component will be the derivative with respect to x, which in this case is 2x. The y component will be the derivative with respect to y, which in this case is 8y. And the z component will be the derivative with respect to z, which in this case is 1. And then I'm going to take that gradient, I'm going to evaluate it at the point that I care about for this particular problem, 1, 1, 5. I am going to get the vector 2, 8, 1. And I'm going to call that my normal vector. And that's what I need. Given a point that the plane is going through and given a normal vector to the plane, I can write that the equation of the plane is the x component of the normal vector times x minus the x coordinate of the point I care about, plus the y component of the normal vector times y minus the y coordinate of the point I care about, plus the z component of the normal vector times z minus the z coordinate of the point I care about, and set that equal to 0, and that's my equation of the plane. I could clean it up. Sometimes it's better to distribute here, clean things up, get a nicer looking result. So 2x minus 2 plus 8y minus 8 plus z minus 5 equals 0. 2x plus 8y plus z is, let's see, we have 5, 7, 8, that's 15. Is this version or that version better? I don't know. It depends on the context, on what you are trying to do with it. But it is two different ways of writing out the equation. They both work, and depending on context, one or the other might be useful. All right, last thing I want to do before I wrap up on this problem is jump over to GeoGebra. And you can see here that the kind of blue shape, which is actually mostly hidden, but if I scroll around, you can see it a little bit better, is our original surface. It's an elliptic paraboloid. The red shape is our tangent plane, and I have in yellow the point where it is tangent. So we can look at it, we can tilt around a little bit and get a sense that yes, in fact, that is the plane tangent to the surface at that point. Right, so that gives us a couple of tools to play around with, a couple of things that we can look at in trying to build this up. And again, we can just spin that around and try to get a good sense of how that plane is supposed to work. All right, jumping back over to my notes, let's wrap up as we normally do by giving you one to try on your own. All right, so I'd like you to find the equation of the plane tangent to the surface that's defined as the equation z squared minus 2x squared minus 2y squared equals 12 at the point 1, 1, I'm sorry, 1, negative 1, 4. All right. So take a few minutes and work through that. If you want, I encourage you to graph the equation of the surface, graph the equation of the plane that you come up with, verify that they are tangents. Sometimes that helps in problem solving. At the very least, it helps in verifying. But work through, find the equation of that tangent plane, see what you come up with, and I'll see you in the next video.